many of you, like me, stare down this problem and I'm just not ready to leave it yet, thinking something is wrong? Part of being a good mathematician, part of being an excellent chemist is admitting your mistakes and going, there is no way a final temperature of a water solution is going to be 156.3 degrees Celsius. That solution would be boiling. I don't even think we could get water that hot by simply just doing a little acid-base chemistry. I suspect I have to back the bus up and try to find my error. Here's what I think happened. When I started the equation in my head, I dismissed the like number of moles of acid and base and simply told myself that there was no limiting or excess reagent. That's simply what it tells me. But I think that's wrong. And here's why I'm thinking that. The mole of sodium hydroxide given to us for the delta H of a reaction assumed 1 mole. We didn't have 1 mole sitting in our cup. We have to kind of think about the term molarity. I'm going to just cover this up and I'm going to talk through the strategy again. In other words, if I had a whiteboard, I'd erase it and start over with you. Clean sheet of paper, and let's revisit our equation. And we need to get this right so that it makes sense. Get rid of this pen. HCl with NaOH, acid-base chemistry, will produce a water molecule and sodium chloride, NaCl. Important to note, the delta H for the reaction says, when this occurs, negative 57.2 kilojoules of heat are released for every 1 mole of sodium hydroxide that reacts. That's what the sentence is saying. Here's what I also know. I have 50 milliliters of HCl. Its concentration is 0.250 molar. And we have 50 mils of sodium hydroxide whose concentration is 0.25 molar. Last chapter, we spent some time with a round little buddy for molarity. Moles per liter is big M molarity. Molarity times liter gets me the number of moles. That's what I need to find to convert this into moles of NaOH. I'm going to take 0.25 molar and I'm going to multiply it by 0.5 liters of solution. 0.25 molar times 0.05 liters says this reaction is being carried out with 0.0125 moles of NaOH. And since it's the same values for acid, we were correct in assuming there's no limiting and no excess reagent, but let's use the volume times molarity to actually put it into moles of reactant and moles of base. Then I can revisit this value here, the delta H for reaction. Negative 57.2 kilojoules would have been released if we used a whole mole of NaOH, but we did not deliver a mole. We only delivered 0.0125 moles. How many kilojoules of heat were released for the small amount of base and acid we added? 57.2 times 0.0125 tells us 0.715 kilojoules of heat were released for this particular equation. And again, released, so I'll show it's negative. Now I can go back to the MC delta T problem and work it with the correct joules of energy. I'm going to multiply this by 1,000. Maybe you just want to slide that over in your head. 7150, again, if that's something you'd like to see hit out. 715, joules of energy. So that allowed me to get rid of the decimal, put it into joules. 715 joules of heat is equal to the combined mass of the solution, 100 grams. Water is our solvent, so 4.18 joules per gram Celsius. And now let's solve for a delta T that's going to make sense. Again, the conversion using molarity times liter helped me convert the kilojoule into an appropriate number for the small amount of reactants we added. We did not use entire mole values. So a little algebra. Let's hit 715 divided by 100 divided by 4.18. This number makes so much more sense. The delta T, the change in temperature, 1.71 degrees. If the water started at 19.5 degrees, our problem read for us, and again that's being pulled from up here, 19.5. The final temperature comes out to be 21.21 degrees Celsius. That makes so much more sense because water should warm up a little. It has such a high heat capacity. When I saw in my last practice where I had water ending up at 150 degrees, I knew I took a wrong turn. That number just did not make sense. So back to the drawing board we went, and we corrected the problem. Using molarity times liter to find the correct number of moles, we adjusted the kilojoules for the amount of reactant we used. That kilojoule was changed to a joule, and again, 0.715 kJs changed into 715 joules. That becomes the heat energy. We set the MC delta T. How much heat did the water absorb? That was 715 joules. Divided by the mass of the combined solution, divide again by the heat capacity of water. The water changed a little by 1.71 degrees. This number makes so much more sense. 21.21 degrees Celsius, the final temperature reading on that water.